In this lecture, I will go over the homework that follows the lecture 16.1 that focuses on the topic of computing the work done by a force, which is one of the main applications of integration in physics that we learn in this class. And as always, I hope you watched the lecture. I will insert it here, but let's go ahead and jump right into the homework. And the first question is we need to find the work done by a force, and in this problem we have a mass, we have gravitational constant given to us, and we're lifting the box 9 meters, so this is the displacement. And it's a very simple problem. Here's the picture. We're literally taking the box and we're lifting it 9 meters above the ground. And since the mass of the box doesn't change, it's a constant force problem, so the force will be simply equal to m times g, and then the work done by a force will simply be equal to the force times displacement. So the final formula that we will be using is this. So throwing everything in, we get 9 times 9.8 times another 9. We have a lot of 9s here, and I'm just going to put it in decimals. So 9 times 9.8 times another 9 is 793.8 joules, and that's the answer. We don't have to round here, so let's move on. We have another one. In this case, we're given the weight of the box in newtons, so it is the force, that constant force, and the distance is still 9 meters, so the formula for computing the work will simply be force times distance. In this case, it will be simply 124 times 9. So, and this time it's not joules, it is no, it's still joules, right? Because we have newtons and meters, so these are still joules. For a second I thought it would be feet, pound-feet, foot-pounds, or whatever the units are. Now we have a problem where the force is given to us as a function of x, and the problem is set up in such a way that leads us to the introduction of this axis, and the displacement will be from 0 to 7. So that means to find the work, we set up the integral from 0 to 7 of this f of x function, and here's the formula. And to use this formula, we're going to plug everything in. And since the purpose of this particular homework is not to learn any integration technique, I think it will be appropriate for me and for you to use technology as much as possible, so we don't actually get stuck on all these minor details. But in theory, everyone should be able to compute these integrals by hand. They're not any special. So as you use technology, make sure you do know how to compute this by hand. Or don't use technology, do everything by hand. So it seems like this homework is relatively simple. as we're just practicing the idea of computing the work for computing the work done by a constant or a variable force. In this case it's variable, so I'm going to set up the integral like this. And put it in Desmos. And we're done with the first objective. So now we're going to move on to the next one. We're going to focus on finding the work done by a spring force. So let's take a look at the problem. So we have a spring of natural length of 1 meter. So if we introduce the coordinate system, we're going to put 0 at the equilibrium, and 1 meter means this will be -1, and it says it requires 405 joules to stretch the spring to 10 meters, but the question says calculate the work required to stretch the spring from 3 to 8. So to calculate the work, we're going to use this formula. And have to be careful here because as we're stretching the spring from 3 meters, so it already has a meter here. So stretching it from 3 meters means we're going to be stretching it from actually x being equal to 2 to 8 meters. So if 8 meters means we're going to go another 7 here, right? So 1 plus 2 will be 3, and 1 plus 7 will be 8. So B will be equal to, oh, way off here. So we're going to, oh no, that's right, 7 meters. So B will be equal to 7. So we're going to be integrating from 2 to 7 the force function with respect to the x, but the force function is equal to k times x according to the Hooke's law, but we don't know k, right? So here what we're going to do is we're going to pause. We're going to hit the pause button here on that solution, and we're going to focus on finding k. So to find k, we're going to use the fact that it requires 405 joules to stretch the spring to 10 meters, but 10 meters in this case is the additional 9 meters. So according to this, let me actually move this down because it's one line of reasoning here. That means k will be equal to 405 over 9. So 405 over 9, it's 65 newtons per meter. And now that we found k, we can go back to the original solution and continue it. So we're going to have an integral from 2 to 7 of 65x dx. I'm not going to do it by hand, although it's easy. It's just a polynomial function, but just that's not the objective of this homework. So let's just throw it inside, and this is the answer. And the units are joules. I'm curious what we did wrong. So the work is required to... So if we're stretching the spring from 3 to 8, in our coordinate system, that means from 2 to 7, which is fine. Is that what I entered? 2 to 7. And did I divide wrong? 4 or 5? What's 4 or 5 divided by 9? Oh my god. I guess... next time I'll use a calculator. So the answer is... let's double check, right? So we're gonna have 45 here. So the answer is 10, 12. What exactly was given? The mistake I've made was I misinterpreted the what's given. So here, when I put, let me explain it to you. When I put f is equal to kx, I misread it. I, for some reason, thought the force needed to hold the spring at 10 meters is 4 or 5. So that was totally my fault. It's not the force needed, it's actual work. So this is how you would set up this equation. It's going to be the integral from 0 to 9 of kx dx, and 4 or 5 will be... let me write this out nicely here. That's a good lesson. It would be 4 or 5 joules is the work. And here you would have to integrate this, right? Because it's going to be k over 2x squared from 0 to 9. And using this, we can find k. I guess we would use the fundamental theorem of calculus here first. So it will be 9 squared minus 0 squared. And now using this, we will find k to be equal to 81 over 2. And now when we set up the final integral, it will be 81 over 2x dx. And then when we come back here, we will have here 81 over 2. That's not what the answer tells us, right? What is it, 225? What did I forget? I forgot the 4 or 5. What am I doing? Oh, this is totally what I didn't want to do. But here we have 4 or 5 equals 81 over 2k, meaning k will be equal to 4 or 5 times 2 over 81. So it's going to be, what's 4 or 5 times 2 over 81? That's just 10. So once we find k to be equals to 10, I guess that's what you get when you are in a rush. and I'm sure you guys can relate to that. This is exactly what happens when you're trying to get through your homework as fast as possible, making these little tiny mistakes that now means I have to do more work. All right, so let's do number 6. Never again will make a mistake like that. A force is required to in a position. Okay, so now we have a force. Okay, this time it's a force. So we given 12 newtons. Well, negative 12 newtons is equal to we have a force of negative 12 newtons that we need to keep the spring in a position compressed negative 1 meter. So that means K is 12. So we do all this work to find K. Now to answer the question, how many joules is done to stretch, how much work in joules is done to stretch the spring, we set up this integral. It's going to be the integral from 0 to 9 of 12x dx. And the answer is 486 joules. So this is the problem that I confused the previous one with. Let's do number 7. So now you see how we have 180 joules is work to stretch the spring 7 meters. So that means if we set the work equal to the integral from a to b of kx dx, we're going to use the first fact to find k. So we're going to set up the equation as 180 joules is needed to stretch the spring to 7 meters. So we're going from 0 to 6, and it's kx dx. So that means 180 is equal to kx squared over 2 from 0 to 6. Let me just write it as a single column. Which is, I guess I can just keep writing it here. Kx squared over 2 from 0 to 6, which is k times 6 squared over 2, which is just 18k. And that means k is equal to 10. And now, to answer the question, we're going to set up the integral from 6 to 7 meters, because the natural length is 1, so we're going to go from 5 to 6, and we're going to integrate 10x dx. The answer is 55 joules. We have another similar problem. That's what I get for not answering it correctly the first time. Same thing, we're using the fact that the work is equal to the integral from a to b of kx dx. So to find k, I'm going to use the fact that 180 joules is equal to the integral from, again, here's the picture, right? So we have the spring, but the spring itself is 4 meters. So if you want the spring to be 7 meters, your x has to be equal to 3. If you want your spring to be 11 meters, then your x has to be equal to 7. If you want your x to be 10 meters, then if you want the length to be 10 meters, then x must be equal to 6. So the integral from 0 to 6 of kx dx is equal to 180. So it's going to be k over 2x squared from 0 to 6. So it's k over 2, 36. So k must be equal to 10. And to answer the question, we set up this integral. We're going to be integrating from 3 to 7, or we're going to integrate 10x dx. The answer is 200 joules. This is a force, so force is equal to kx. So to find k, we're going to use the fact that negative 72 newtons are needed to compress the spring by 4 meters. So k will be equal to 18. Never again I will make this mistake. Yes. And now to set up the integral, to find the work, we're going to set up an integral. We're going to be integrating from 0 to 9 this function. So the answer is 729 joules. Alright, so it looks like we completed this objective, and we're going to move on to the next one. So now we're going to be lifting a cable. So let's read the problem. We have a cable of length 3. So we have a building. We have a cable of length 3, so we're going to set up the coordinate system, and we're going to go from 0 at the bottom and positive direction to the top. So the height is 3, and the mass is, let's say it's a bucket, is 48 kilograms, and I apologize, we don't have a bucket. It's the weight of the cable, 48 kilograms. So this entire cable is 3 meters long, but it's 48 kilograms. So what we want to do here is we want to find its linear density. So let's call it rho. And the linear density of this cable is 48 kilograms per 3 meters. So it is 18 kilograms per meter. And as we're lifting this cable, we're going to pick some arbitrary value of x, and at that value of x, we're going to be lifting the cable delta x. So the weight of the cable that's still left hanging when you already x units above the ground is going to be this, which is naturally equal to 3 minus x. And that means the force needed to lift that much cable by delta x is, well, delta x is not part of the equation yet, but it's going to be 3 minus x times g. So the work needed or done by lifting that cable will be F delta x. So it's going to be 3 minus x g. I guess I don't need to rederive this formula because we already have the formula. Like, once you know your formula for F in terms of x, which is what we have, to find the work, all we have to do is just set up the integral from a to b of f of x dx. In our case, a is 0, b is 3, and the force lifting the cable is 3 minus x times g dx. That's it. And I'm not going to be doing it by hand. So the answer is 44.1 joules. What I did, I forgot the density, right? I just computed the length, so this is how many meters, but we need to multiply this by the density and then by the gravitational constant. So I'm missing this whole coefficient 18, so it's going to be everything times 18. So the final answer is 793.8. And I don't know what to do with this type of errors. I can say that I'm making it on purpose, so I can just show you the correct way to handle such mistakes, because they are inevitable. But that would be a lie. Pretty much digging myself a hole over here, because now I'm gonna be forced to do more problems of this type. And let's do number 11. In this problem, we have a bucket. So first thing we do is we set up the coordinate system. 0 at the bottom, 16 meters at the top. And we have a bucket hanging off here attached to the cable. The bucket has a mass of 21 kilograms, but it leaks sand it has an extra cable here to attach the bucket, and density is 2 kilograms per meter. So let's set it up. So the way we're going to set it up is we're going to separate the bucket from the cable. This is the formula for the work, and the force needed to lift a cable when you are X units above the ground can be found using this formula. We have this much of a cable left, so it's going to be 16 minus X times the density, which I forgot the last time. The density is 2 kilograms per meter times the gravitational constant. So this is the amount of force needed to raise the cable when you are already X units above the ground. Now, to find the formula for the bucket, here's what we're going to do. The initial weight of the bucket is 21 kilograms. And also, I forgot, we don't have 16 here, right? Remember, we have that plus extra meter of cable at the bottom, right? So it's 17 minus X here. Now, the force needed to raise the bucket at this, when you're already X units above the ground, it can be found by this. So initial mass of the bucket is 21 kilograms. Now it's been leaking 0.8 kilograms for every meter. So by the time you get to X meters above the ground, you're going to have minus 0.8 times X kilograms of sand leaked out of it. So this is how much you have left. And we multiply that by gravitational constant, G. That's it. So the integral that computes the work is from 0 to 16 of 17 minus X times 2 G plus 21 minus 0.8 X times G dx. I'm not going to do it by hand. That's what Desmos is for. So let's type this up. And we can just move G to the front and not make it part of the equation, but here we have 17 minus X times 2 plus 21 minus 0.8 X, and that's the answer. It's going to be 5111.68 joules. Another problem, but this one just has a cable. So we have 3 meters, set your x-axis, mass is 30 kilograms, so that means density is mass per length, so it's going to be 10 kilograms per meter. So when we are, here's the cable, when we are X units off the ground, we lifting 3 minus X of cable here, so the amount of work, so the force required to lift that much cable can be computed by 3 minus x, that's the length, times rho, that's the mass, times g, that's the force. And to set up the integral now, all we have to do is to integrate from 0 to 3 minus x times 10 times g dx. Let's have Desmos do this. I'll just copy this over here. It's going to be integral from 0 to 3, and we have 3 minus x times 10, and g is out, so the answer is 441. We have a similar problem. We have a building, we have a cable, we introduce the coordinate system from 0 to 17 would be the limits of integration. The mass is 34, the length is 17, so we find rho as 34 over 17, which is 2 kilograms per meter. Now, at some arbitrary point x, when there is this much cable left, we're going to find the force as a function of x to be 17 minus x times 2 times g. So the work done by a force lifting this cable will be the integral from 0 to 17 of 17 minus x times 2g dx. Put it in the calculator. And here's the answer. Have 2-meter tall building, introduce the coordinate system. These are the limits of integration. Lifting a suitcase. So suitcase is 26 kilograms. We have additional 2 meters of cable to secure the suitcase. Cable weighs 16 kilograms. So the density of the cable will be 16 kilograms divided by 2 meters. That's 8 kilograms per meter. But what's more important here is that the work done by the force lifting this setup can be found by using the integral from a to b of the force needed to lift the cable and the force needed to lift the luggage, let's call it a bucket. And to find the force at some arbitrary x needed to lift the cable we've done it multiple times. It is the 2 minus x times the density times the gravitational constant, and the force needed to lift the bucket can be computed by, and I again forgot those extra 2 meters of cable, but the force needed to lift the bucket is the mass of the suitcase, and it doesn't look like the suitcase loses any mass here, so the mass will be constant, but to make it into a force we have to multiply it by the gravitational constant. So the work will be equal to the integral from 0 to 2 of 4 minus x times 8g plus 26g dx. Not doing this by hand. I already have kind of a template over here. So this is 4, this is 2, this is 8, g is outside of the integral, and here we just have 26. So the answer is 980 joules. And we finished this objective. So let's move on to the next one. In the next one, we'll be doing the pumping. So we're going to be computing the work done by pumping liquid out of a tank. And let's go ahead and read the problem. So we have a cylindrical tank. We're going to introduce the coordinate system going from the top down. And so the radius is 5 meters. The height is 14 meters. But it only starts at 7 meters. So this is the initial level. And everything is given. So from the lecture, recall that to pump a liquid, we're going to integrate from the initial level to the end level. And what exactly are we integrating? Well, we're considering at some arbitrary x, we consider the layer of water of width delta x, and the weight of that much water is found using this formula. So we take the volume, which is equal to the area at x, we multiply it by the delta x, which eventually becomes d of x, then we multiply it by, so volume, we multiply it by density, that makes it a mass. We multiply it by gravitational constant, that makes it a force. And we multiply it by the distance need to be moved, which is the depth level, which is x. And this gives us the formula for finding the work done by pumping. And in this formula, the only thing that we don't know is the cross section immediately, right? So that's not obvious. However, in the case of a cylinder, the cross section is as simple. To find the area of the cross section means to find the area of a circle of radius 5. And notice how it's actually a constant, so it's not changing whatsoever, which means we're pretty much done. We're ready to set up the integral. We're going to be integrating from 7 to 14. We're going to be integrating 25 pi times rho. Rho is 1000, g is g, and x is x. So this is the integral that we have to do, and as it's been the case in this homework, I'm not doing this by hand. So we're gonna have this integral. That's the answer. However, we do in kilojoules. So if we're going to use kilojoules, then this is the answer. So these are joules, these are kilojoules, but we also have to round to the nearest kilojoule, so here's going to be the answer. We have a tank inverted circular cone. We set up the coordinate system. The radius, so the height is 16, means this is 16. Base radius is 6, so this is 6. Tank is full height 13. 13 means this is the initial point. And we're going to be looking at some arbitrary x. And we're going to be looking at this layer of water. And according to the formula, the work done by pumping will be equal to the integral from A to B of, and we're going to start with the cross-section area multiplied by delta x, which will become dx. Then we multiply it by rho to make it a mass. We multiply it by g to make it a force, and then we multiply it by x to make it a work. And in this formula, what we don't know is the cross-section, so this cross-section, as a function of x. And now it just becomes a simple geometry problem. Let me just draw this line. So the cross-section area will be equal to pi r squared, but r depends on x. How exactly? Well, let's find out. When you are x units deep, you're going to get this radius. But when you are 16 units deep, you're going to be all the way at the bottom. And when you are 0 units deep, you're going to have the radius of 6. So in this picture, we have two similar triangles. So we're going to set up this proportion. 16 minus x over 16 is equal to r over 6. So r is equal to 6 over 16. 16 minus x. That's r. So the a, which represents the cross-section, will be equal to pi times 6 over 16 times 16 minus x squared. And now we're ready to set up the integral to find the work. It's the integral from 3 to 16 of pi 6 over 16, 16 minus x squared, times rho, which is 1000, times g, which is gravitational constant, times x dx. Not doing this by hand, obviously. So let's put it up in Desmos. And looks like I've set it up correctly. So here's my answer: 19816516605. These are joules. In kilojoules it will be, this is kilojoules, and if I have to answer to the nearest kilojoule, it will be 19816.817. Similar problem. So another cone, but same coordinate system. 0 is at the top, pointing downwards. The height is 19. The radius is 3. The field with water height 4. So 4 means we're gonna go from 15 over here. And same thing, right? So we're going to be using this formula in which we're going to consider at some arbitrary level x a layer of water of width delta x, and the mass of this water can be found by looking at the cross-section area times the height, which becomes dx eventually, and then multiplying it by that's the volume, multiplying it by density gives us mass, multiplying it by g gives us force, multiplying it by x gives us the work. Now to find the cross-section, we're going to use geometry. I'm going to draw this triangle here, and we're going to acknowledge the fact that the cross-section is equal to pi r squared, but r, as the radius of this little circle, changes depending on where you add. So at the beginning it's 3. When you are x units down, it's going to be r. So this will be, this side will be 19 minus x, and the total is 19. So using geometry we can set it up as a proportion. 19 minus x over 19 is same as r over 3, meaning r is equal to 3/19 of 19 minus x. So the a of x is equal to pi 3 over 19, 19 minus x squared. So to find the work, we set up the integral to go from 15 to 19, and it's going to be pi 3/19 19 minus x squared times rho times g times x dx. Not doing it by hand. And the answer is 26199,316 joules, and kilojoules will be 261 point let's say 99 kilojoules, which is rounded, will give us 262. I assume one more problem. And of course, cylindrical tank. After dealing with inverted cones, I think going down to cylindrical tank is pretty straightforward. So we have a cylindrical tank, meaning it has the same area at any level, the same area of a cross section. So the radius is 2, the height is 13, so we set up the coordinate system. This is 0, this is 13, and the work will be done by computing this integral from a to b of the cross section multiplied by the height, which is delta x at some level x. So eventually it will become dx, and then we multiply by the density, then by the gravitational constant, and then by the height. But in this case, a is constant. A is just equal to pi r squared. R is constant, so the area is always 4 pi. So it doesn't matter at which level you are, you're always going to get the same cross section. So the integral that we need to compute will be from 8 meters. So 8 meters here means we're going to start at, let's say, 5. So we're integrating from 5 to 13. 4 pi, rho is 1000, g is g, x is x, dx. So this is what we integrate. Let's put it in decimals. From 5 to 13, 4 pi that's it. This is joules, and in kilojoules it will be this. Rounded to the nearest kilojoule. And we completed this objective, and therefore we completed this homework. And if you have any questions about how to use integrals when finding the work done by a force, feel free to reach out to me.